Okay, I think we are alive now. Let's just see. Yeah, so wait a minute. Come on. Just let's just do this. So where am I? Okay, I hope you can hear my voice clearly. Let's just start live stream in Twitch as well. Let's just start the stream in Twitch as well. We are connecting. Few seconds after we will live in Twitch as well. Yeah, we are now live on YouTube and Twitch. Incredible, right? Okay. So now, so in our previous live, we just covered a lot of things about Rust using this book called um, Rust book. So this is the book we have used for Rust and to learn Rust. Okay, so I think we just covered up to enums. I think we did touched this chapter, but this is new. We haven't touched this chapter yet, but today I just want to focus on another thing where we actually build some project in Rust. So instead of just studying about Rust, I think we can just build something in Rust. Okay, so for that, I already I already wrote this code with AI. So actually, I'm not wrote this code. I'm not the one who wrote this code. Actually, the I use I think it's a Gemini. So that's a pretty good model in coding. So I used it. So basically, so what I want is to create. What I want is to create a GPT. Do you know GPT? It's basically a base for current ChatGPT model. So current ChatGPT is pretty more complex than previous GPT models. So I think first they created GPT-1, then GPT-2, then GPT-3, and okay, let's just share. Wait a minute. So so that's it. So let's just so actually the current GPT is not it's now it's a GPT 4 right? So current GPT is of a GPT 4o. There is they have a lot of other models as well, like O3, O4. They are thinking models, right? So GPT 4o is not a thinking model. It's not a reasoning model. It's a normal model. It's not reasoning model. But first, this entire GPT thing is started from 2017 or something like that. Um, I don't know the exact number, exact year, but it's somewhere between 2016 to 2019. So first they released the company. So actually first they released this GPT-2. So first they released GPT-1, then they released GPT-2. I think GPT-1 is not open weights, but GPT-2 is an open source model. Mm, Basically, open source what I mean by that is their weights are fully opened. So you can experiment, so you can use it. So you can here you can see it's about to 6 years ago, basically meaning that 6 years ago. Now it's basically meaning that it was released in 2019 or something like that. Okay, so they released this model, and actually this model is comes with uh, GPT. Lightman. They released some paper with that. I think this is this a GPT-2 paper. Yeah, yeah. This is the GPT-2 paper. So these are the authors who created that, and this is came from OpenAI in 2019, I think, and they released it's basically whenever some company released some AI model, some deep learning model, they will not just release a single model. They released a series of model. They call it as a family, right? GPT-2 is a family of models. So basically what I mean that actually they released a four model, so which is first one is 170 117M, basically 117 million parameter model. But this thing is actually not true. They just basically they just mistakenly they actually did mistakes with counting the actual parameter count. So it's actually it's not 117 million. It's actually 124 million model. And another second model is you can see. So second model is 345 million, and third one is 762 million, and fourth one is this is the largest model at the time. This is the state of the model at the time 2019. They just released all of the weights open source, so now we can use that. So this model is the biggest model at the time they released. It's a 1.5 billion parameter model. And so these are the metrics. So actually it's not a metrics, it's data sets, something like that. Okay, these are the metrics. And at the time they have a lot of so at the time I don't know with exact number how much token it was trained on, but I think they had it's a common crore. So this is one of the biggest data. It's basic common core is basically a data set where all it's have all the internet. So basically all the web pages or how to say all it's basically having all the contents in internet full of text data. It's not image or something like that. It will have a full of it has a full of text data. So but it's not a perfect or perfectly clean or pure data. It's full of text data without any um how I put this, without any sort of filter used in that. It's kind of just a data. It's just a huge amount of data which have I think it's mostly English. Yeah, it's fully English, I think. So they used this data set for train the model common core. Actually nowadays there is lot of variants of this data set which is really how to say really high quality, with really have tokens with a very high quality, and filtered with both humans and AI, and basically saying basically increase the quality of this data set. So common crawlers have, yeah, it's about 240 GB of text. So it's a huge number of data. And so it's it's contained Wikipedia text, web text, and newspapers, and lot of things. It's a huge amount of data, but it's not very highly quality. Highly, it's not very high in quality. because it's just a collection of huge number of data. So it both have faulty and all the information. So but nowadays there is a lot of variance which is basically filtered from the common tool, basically increase the data quality uh, by both using by AI with some other parts are created by created and inspected and maybe deleted by humans. So there is a lot of data set nowadays, but in 2019 this is what they have at the time, what they had at the time. So they used this, and it's not really easy for to train a model. So it's really hard to train a model like this with this size at the time. So it's really hard for them at the time. Nowadays you can do this very easily, and nowadays you can do this if you have some amount of GB or something like 3080 GTX um, 3080 or 4080 or somewhere something like a high GPU, and you can do this. You can create a model like this, but it do take time. It do take some time. But if you want to really if you want to produce this model in a short amount of time, you can use some cloud, something like there is a lot of cloud, Google Cloud, Amazon, Lambda. So there is I think I'm not sure. I'm not done this before, but there is this person called Andre. His name is Andre Kapat. So um he's extremely talented person, and he's he's a computer scientist, and he's one of the members who founded OpenAI. He's a co-founder of OpenAI. I'm not sure now he's still a co-founder of OpenAI, but he really founded the OpenAI, and he is the reason behind he's the person behind autopilot as well, Tesla autopilot. um, he lead the team, I think, and he formerly worked as OpenAI, co-founded it, and he's really a great person. And he so so this person, he just wrote this entire thing, so we can GitHub. So he just wrote this entire thing in both C and Python. So actually he did that in his YouTube channel. I think you can, if you search for Andre Karpat in YouTube, you can find his videos about these things. So this is one of the implementation. So Nano GPT. So it's basically a pretty old implementation nowadays. I think, yeah, it's 2 or 3 years ago. But he basically implemented this GPT-2 in fully using Python and PyTorch. So this is what he just did. So he used PyTorch and Python, and next he actually created another project called LLM.C. So this thing is This thing is really wrote in entire GPT implementation in C and C++. So here you can, where is it? So, okay. So here you can see that this entire thing. So this is the result. This is the actual model configuration settings. He just used number of parameters and maximum sequence length, vocab size, number of these kind of things. So he also did wrote an implementation for just for CPU, but I don't know whether it's a good idea to create this size of a model in a CPU. But it takes you, if you, even if you did that, it will take you huge amount of time, but you can do that. So CPU are really not good at parallel computation. Basically, if you have a huge amount of data and you want to basically done some operation in it, and CPU is not a best candidate for it. GPU is a best candidate for it. But when you compare the speed of those things, CPU is a little faster. CPU is the actually fastest chip, but GPU is it can handle huge amount of load in a same time. It can do huge amount of operation in a parallel. So that's why GPU is very important for any sort of thing. If you are doing creating a model, fine tuning a model, or um, any sort of thing you are doing, whether any sort of thing, if you want to do something in a deep learning, you pretty sure end up with the GPU to create those models, because it saves you a lot of huge amount of time, and there is a lot of benefits in it. But if you do this in a CPU, it's going to be take a lot of time for you, and I'm not sure about that, but I'm sure it will take huge amount of time than a GPU. But I'm not sure whether you can create a model like this in a CPU. So CPU is extremely fast at series of operation, not a parallel operation. So if you have a series of operation, it's extremely fast, and you can use it whenever you have a series of operation. For parallel operation, GPU is the best one. And so he wrote this thing, and he wrote the entire thing in C and CUDA using. So if you have a NVIDIA GPU, you can use this. But if you have another one called, I think it's AMD, right? It's a Let's just see. Yeah. So if you have any type of GPU which is not a NVIDIA brand, so it's going to be a bit trouble for you, because this entire thing wrote in C and CUDA, I think. So they used some of the libraries in CUDA. So CUDA is basically where it's kind of like entire software for GPU programming. So you can do a lot of stuffs with the CUDA. So it's like a very efficient and optimized implementation for GPU operation and GPU sort of things. So if you want to write your own kernels, like optimize the matrix multiplication or any sort of things you want to do with GPU, um, specifically for NVIDIA GPU, right? NVIDIA GPU, so CUDA is for NVIDIA. So they created, still CUDA is maintained. It's not open sourced. CUDA is maintained. It's open sourced, but it's still maintained by the NVIDIA. So If you have an NVIDIA GPU, you can use CUDA, those libraries, sort of things. But if you have other sort of brand GPUs, uh, you need to look for their software, right? So something like that. So these are the things you keep in mind. So this is basically he implemented everything in C and C++ and CUDA. And so now we are trying to implement this in Rust. So that's what we are going to do. And I'm not sure whether we can do this in a single live. It's going to be much harder for us. So still is because if you are using some kind of a library or so something wait a minute. Let me show. What is that? So he did use the library, he did use the framework called PyTorch. So that thing is really PyTorch is one of the greatest framework in deep learning ecosystem, and another one is TensorFlow. But in my opinion, PyTorch is a very beginner friendly and very convenient, and it's very simple to use. You can say uh, so it's really very simple to use PyTorch, because their APIs are very concise and easy to use. So they do have a lot of things for basically for optimizations. So if you wrote everything in a Python, just pure Python, it's going to be um, so the reason why why you need to use these kind of frameworks is because their implementation is very optimized and efficient, so that you don't have to worry about the wastage of compute and the wastage of memory. You don't have to worry about that. So their implementation is much more optimized and production ready. You can So there is a lot of system nowadays running in PyTorch, just PyTorch. So that is one of the thing we need to seek for these kind of frameworks. But if you are really good at what you are doing, if you know everything about something like um, the architecture you are going to implement and the language you are going to implement, and if you are really into GPU, there is no problem. You can you can write your own implementation in some kind of language like Rust or C or C++. The reason one of the reason he also post the video about how he wrote this, but he doesn't post about he doesn't post the video about how he wrote C++, the CUDA implementation, but he does post videos about this entire PyTorch thing. So he really wrote everything in a way, everything, and show how everything is working. But he also wrote that C, and he basically were trying to compare both things at the same time, is because actually he is writing the entire architecture in Python using PyTorch, and on the other side he's writing everything in C, CUDA, C++, and just see which one is much more faster. And of course C and C plus C CUDA implementation is much faster than the Python. C is basically faster than Python. But so that's really for a bottleneck, that's really for a specific use case. Is because you cannot write everything, you cannot write everything you cannot replicate everything in C, just it's it require a huge number of peoples and huge number of time, right? You cannot wrote entire PyTorch in a C or C++. So it's going to be a huge amount of time. So huge amount of energy, huge amount of time, huge amount of people you need that. It's PyTorch is I think it's you know even millions of lines of code nowadays. So it's really hard, but they do provide a lot of APIs for other languages, C, C++, or something like that. uh, so the reason why we are people write a custom implementation in language like low level language like C is because you can get the advantage there is a advantages there is advantage there is a number of advantages you can get when you write something in a low level language. So is because fast and efficient, and you can basically write you can basically do what sort of things you really want. So even you can write your own optimized implementation. You don't need to rely on other frameworks or other type of any of things. So now in our case GPT-2 is a very simple model nowadays. It's a very small model nowadays because current AI models are like a trillion size of parameters in size. Even Llama 4, I don't know, I just forgot the exact name for it, but they do release they do have a plan to on the mm, I think it's a trillion size of model, so still a trillion parameter size model. And nowadays most of the models are in billion size. Million size is much rare. But for text, for video, image, these kind of things, million and few billions are really good, really good. But for text, it's a total it's a different story, right? For text, if you want to a really good model, uh, text based model, you would at least need to have somewhere around 30 to 50 billion for us decent with the decent performance, right? So nowadays state of the models are billion trillion. So compared to that, these models are nothing. So these are very small models, so you can write everything in a so here I think he did write everything in just a single 860 line. um but I guess it's the total number of lines is about to 1200 or something like that. So he did everything from GPU support to CPU support. So he wrote everything from CPU to GPU support. Mm. So that you can all you don't need actually, if you download this file, and all the thing you just need to have is just some GPU. If you have, if you don't, you can follow the CPU implementation. If you have a GPU, all you need to have is you don't need to have anything at all. You just need to have this single file going to train the GPT-2 model. So it's really very convenient and simple to use. Is because you don't rely on any sort of things, and you are not going to get any sort of error because everything is created in very optimized implement. Everything just created in pointers, integers, floats. So it's not, they're basically using floats and pointers. That's it. So but That's it. So now, so what our goal is to create this entire implementation in Rust, so that we can understand Rust more deeply, and we can learn some AI. So I don't know how he really handled the tricky part is that when you really wrote a custom implementation, and you need to keep in mind that you can wrote the implementation efficiently and easily, but the problem is you need to create this grad engine. It's basically where it's a backward pass. So it's basically what it's basically doing is it's the actually engine thing. You can think of it as like where it's basically doing the it's calculating the gradient for each nodes in that neural network. Uh, so that thing is really complex to do, but I don't know how he really handled that. But I'm sure he wrote the gra he wrote the backward grad engine in a C, I think. Let's just see. Let's just see. We can find that. So these are he just created tokenization and data loader in a separate file and utility. So but I think he just I'm not sure how he really calculate the gradient for these things. It's a uh, it's a pretty complex implementation, I would say. It's not it's a fair level of complexity. They have a fair level of complexity. I think he wrote everything in a single file, even gradient engine, grad engine. I'm not sure whether he using another file, but I think 80% he using the grad engine in this file, merging them. So just okay. Mm. So that's the thing we want to implement. So we are going to use AI, both AI and some part of code we are going to wrote, and some part of code it's going to be wrote by AI. So I think it's sorry for that. I think it's both fun and going to be fun, I think. So this is one of the tensor implementation. So here what we have is, So this thing called struct. Okay. So this is basically the tensor we are going to use, right? So we are creating a custom data type using custom data type using struct. So it's going to be have we are going to use this vector data type for actual data, right? Actual data value. There is uh, let's just see. Okay, wait a minute. Okay, so I think they have a dark mode. Yeah. So let's just no. Okay. So when we are trying to create, there is three things we need to keep in mind. Is that like okay. So this is a model, and another thing. So wait a minute. Let's just say this is the actual tensor. This is the tensor. So some data type, right? So the let's just this way. So this is going to be a data, and this is going to be a weight. Okay. So first we need to have some data, right? Without this, we cannot do anything. So this is the first thing, and this is the first thing we need to have data. You can implement GPT, you can implement any sort of things without data. But for training, when you are going to actual training, when you are really into training, you need to have some amount of data. Then you have this model. So this is a model. So this is the actual model, and inside of it, it have a weight. So basically, this is model. The word model refers to the actual weights, or maybe the architecture. It's basically depend on the context where you are using. If you are using the model while you are training, is mostly meaning that the actual architecture of the model. And if you are using after the training, I have this model, means actually you are going to have a weights of that model. That's what you are actually meaning. So it's basically depends on the context where you are using. But so the model is, so the first thing we need to have is a data. The another thing we need to have is a architecture. So the architectures, there is a lot of huge amount of architecture, but one of the greatest architecture now in AI is a transform architecture, and everything is basically built off of it. Nowadays they have a lot of new architecture came into play. Mamba and Reformer are a huge amount of architectures, and basically they are basically just how to say, they are basically changing parts with the architecture, something changing some other parts in transformer, something like attention. And they have nowadays deep seeks are using multi-latent attention. Those attention are really good, and compared to the previous attention, so multi-headed attention. So those things, there is huge number of improvements are done this basically transformer architecture. But this is the beginning point. uh, this is the beginning point. So the transform architecture. So this is the beginning point of really, I would say this is the beginning point of the boom in AI, right? 2018 to the boom in GPT, everything is basically built upon this architecture. So it's really good. And so GPT-2 is a very simple architecture. It's a GPT-2 is a pretty um, same architecture, which is actually this architecture came from Google. So maybe I can say this. Can, all you mm, all you need to know the paper is, all you need something like I just forgot. uh, Transformer, all you need is attention. So this is the paper actually they attention is the attention is all you need. This is the actual paper they just introduce. Come on. So there's all you need papers. Attention is all you need paper is basically where they first introduce this transformer architecture. So before that, it was introduced by Google, DeepMind, I think. Um, so this architecture is showing actually shows the potential of deep learning and neural networks. So this is the paper. So here they have a nice diagram. So this is the actual transformer. So this paper is actually came from some machine translation system. So this paper is actually not created for basically their aim is not for creating GPT, nowadays chat GPT like thing. It's a LLM, right? Large language model. But they are yeah, it's actually it's a machine translation paper. So it's the first introduced in a missile translation system, not in a LLM system. So they created this for missile translation. And that's why they have this two kind of architecture here. Input and output. It's actually a two different transformer architecture. So they would call this as a encoder block. This is a decoder block. So but nowadays the current LLMs are not have this kind of architecture, and they have this decoder block and stacked in it. So basically they take this decoder block and only, and throw away this encoder block, and change make some few changes here and there, and stack them, right? Stack them. So then they find out that this thing is really good at producing text. And That's why that's how they actually first they come up with this idea of GPT-1, then GPT-2, then GPT-3, then GPT chat GPT, then GPT-4, and then GPT-4o. These models are basically this is the starting point for all of those models, not only GPT, Claude, Gemini, Llama. Everything is basically nowadays most LLMs are basically based on this architecture. So it's a fantastic architecture. So this is the thing, when you are going to implement something, we need architecture and we need a data, and there is a lot of things we need to take care. Not only architecture, there is huge number of other things we need to take care. What are the functions we are going to use? So nowadays there is huge number of attentions. Back then there is only single attention, I think, multi-headed attention. So this is one of the core mechanism in uh, transformer. um, so there is a huge number of things had changed, and so this is the multi-headed attention, and so that's it. So GPT-2 just use this thing. This There is no changes. I think there is very few changes. So they took this add and norm layer and put it here instead of there, and some other little changes here and there. Nothing more than that. So 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 we need to take care of the data and architecture, then we can train a model. So we need to take care of the gradient engine as well. So I call it as a gradient engine, and most people call it as it's going to be a backward. So it's going to be there is a huge number of variant to gradient descent. Actually, the gradient descent is the actual algorithm behind neural networks, but it have nowadays it have so much variance. Uh, so maybe I can just show you. Let's just so these if you are very beginner to AI, like if you are beginner, uh, to deep learning stuffs and these large language models, it's going to be a bit harder for you to understand, but because why it's going to be a bit harder for you, but just wait a minute. But you can understand a lot of the things, core important things about AI, how current deep learning systems and ChatGPT and cloud, these kind of things, how really works, and types of. So I so this is these are the different types of gradient descent: batch gradient and stochastic gradient descent and mini batch gradient descent. And so these are the techniques, these are the advanced, let's say, types of gradient descent or something like that. So it's basically built off of one gradient descent, nothing more. So Adam, RMS Prop and AdaGrad and Adam W. These are the things used in state-of-the-art systems. So to train state-of-the-art systems, these are the things mostly you can see. Adam. So here you can see that very popular. Adam is a popular. RMS prop also. It's a really good thing, good engine, and Adam W is also, yeah, good. So this thing, you also need to take care of this thing called, maybe we can call as okay, gradient set. There is lots of variant, but you know, as time goes, there is huge number of improvements had been done in these architecture and decent, I mean, gradation and the data. So these are the most important thing. And another thing you need to take care is the type of data what you're going to use. So type of data is one of the really important thing. So this thing is so this thing is really important if you are optimizing your implementation. Type of data is really important. There is it's not type of data, type of number, maybe we can call this type of number. So that is that is we have float 32, we have float 64. If you are using float 64, it's going to be fine, but it requires um, more memory than float 32. And float 64 give you more accurate result than a float 32, but it's really a minor change, minor. I would say it's really hard to notice. Hard for you to notice is basically because the float 32, maybe some of the peoples are doing some of the peoples are really doing cooperation in float 16. Even after the develop after created the model, you need to put it somewhere, right, somewhere in a cloud, so that the user can use it. And they would say using even float, that is has a custom data type like I8, and basically 8-bit number. So those things are used for inference, but mostly when it's comes to training, float 36 is optimal thing. uh, but you do need to have a certain architecture for it. You cannot just use float 16 or something like that. It's really you cannot do that just with the whatever GPU you have. You cannot use you can use any sort of data. But you do need to have yeah, certain architecture for it. Something like my GPU is my GPU is Turing architecture, something like that. So if you have if you can afford some kind of cloud, something like $3 or $4 per, I think $2 or $3 per half hour, and you can get the this A100 H100, these kind of GPUs. They are really good at parallel operations, and they have huge number of memory and on chip RAM memory, so GPU RAM memory or something like that. So those things are really help you to do, but there is certain architectures do have custom built data types for this huge number of parallel operation. So if you have one of them, if you can access one of them, you can use there is you can use a lot of custom data types which are really optimized for these kind of operations. They once you have weights, once you train the model, all the thing you don't need to have the actual training code, right? All you need to, once you have the model, you don't need the data, you don't need a training code, but you do need a inference code. That's bit different than the training code, because there is no backward pass and these kind of things. You need to you need to take out of from your implementation. Actually, after you train your model, you are going to have this weight, and you need to write you need to have this inference code. So this two things is enough for to create this the two things is important. This is basically enough. You can write that's it. That's system AI system. So yeah, you can put it in a cloud, or you use it in your laptop to inference it again. You can do anything you want. All you need to have is the weight and the architecture, the code, inference code. So let's just ask GPT, what are the data types, what are the number types we can use for optimized operation. So float 16, it's a double. There in many language, the programming language, they call this as a double. Float 32 is a float single, and float 16 is a half, and fast GPU and B float 16. So this is one of the custom data type. So for brain float, this is for very optimized and fast operation. So Google hardware stable training. So int 8, it's for inference, mostly for inference, not for training. I don't know, but some company use this for training as well, I think. And int 32 is another thing. So int is basically it's int is basically for you can use it int for inference, but you do need to sacrifice some accuracy for when you're using Believe 416. So this is much more accurate than this, but this is much more faster than this. So it's a trade-off, right? It's a trade-off. So, but mostly B416 is most people use, and F16 also, and but believe I don't know B4 B float 16 is I don't know, this thing is available for old GPU, I don't know, but mostly You can use float 16 instead, but still it's float before 16 and float 16 are not the same thing. It's a different data type. They do have different things when it's compared to when it's come to bit sort of things. But float 16 you can use. The another thing, the data type of number, this is another thing we need to take care of when it's come to implement GPT-2. And another thing we need to take care of is that, so this is tokenizer thing. So that is one of the thing. Another thing you need to take care. It's basically converting the actual data into some kind of a token. Then you can train those token. You can train those token. So just wait a minute. So that is another thing you need to take care. So and these sort of things. So that's it. And so now here we have a 32 basically float 32 value, and we are going to implement our operation for a float 32. Maybe we can change this to float 16 or something like that. And so now currently we are remember now currently we are writing this for GPU, not as CPU, not for GPU, right? It's a different thing. If it for CPU, I don't know. CUDA have some kind of a Rust API or something like that where we can connect to CUDA. I'm not sure about that, but we can just implement this using for CPU. Then we can convert. Then we can find a way to connect to GPU. Okay, so this is a tensor implementation. It's going to be a float 32, and so we have some other methods for it, new, and it's so this thing is basically for um, filling out zeros in array. And I'm not sure I'm not I haven't read this implementation yet. So because before that I just wrote GPT-2 and this sort of things in only PyTorch and Python. So Rust is a bit new for me, and you know that last um, how to say previous live before previous live every last every live we are just learning Rust. So pretty soon we are good at it, then we can write everything by ourselves. So it's a operation thing. So we do have Here we are using the tensor rad, and so I think I thought that it's a good idea to use AI, but writing by ourselves is much more better than using AI. I think when it's compared to learn, when it's come to learning, writing by yourself is really a good thing, because it do give you the challenges and the way to understand deeply what you're writing. So let's just what we are going to do now is let just what are the things, what are the actual thing we need to, what is the architecture we are going to implement. Okay, let's just see that. Then once we finish these what to say, these technical details and concepts, then we are directly jump into the actual implementation. So where we can write code, maybe we can cover this writing code topic tomorrow. So where we can write the entire implementation. For now, let's just take overview how everything works. Okay, so this is the part we are going to implement. So this part, this is the encoder and this is a decoder part. So we only need the decoder, so we don't need the encoder. And so this is the multi-head attention, and these are the add norm layers, and this is a simple sort of thing where you're going to add the previous layer to the new layer without doing any change. Kind of it's relatively easy. So mm, this is the attention. So this is the core part of transformer. And if you want to implement this, you need to have a three sort of matrix. So the one is V, the another one is K, the another one is Q. So this matrix are basically not bias matrix. They are basically for multiplication. So you're going to take your input and multiply it with this matrix, and you can see here. It's first we are going to multiply with Q and K matrix. Okay, then scale, and then mask, and then max, and then multiply with the value. So what it means is basically mask is basically for where you don't want to see the previous next token. It's basically when you're trying to find the next token, you don't want to see the what is the next token. Okay, it's it's like if I'm a number one, I'm trying to find the number two. So which is basically mean I don't have to know what is number two, then only I can find. So this mask layer is basically truncate them. So so that you don't have idea about what is the second one, and then you evaluate them to softmax, then you multiply it with the value matrix. So this is pretty concise, and this is how the entire softmax entire attention works. First we are going to take that input matrix and multiply it with q, k, and v. Then we multiply qk and qk transpose, and then we are going to scale them by square root of dk. Then we are going to truncate them. Then we are going to softmax evaluate them with softmax. Then we want to multiply the value with the attention. This is pretty much up. This is the single formula. That's it. You don't need anything more than that. This is the single formula. This is the actual core thing. Let's say this is the core thing of LLM, transform architecture. And these feed forward neural layers and linear layers are simply yeah, layers of array and multiply with the input we are giving. That's it, nothing more than that. And the softmax we can see. Let me see. Let's see. They have a formula for softmax. I think they have. So this is the optimizer they used in this paper. Optimizer, Adam optimizer. Okay, that's really a good optimizer. And regularization technique, there is there is lot of details and lot of things here we haven't covered yet. There is a regularization techniques we need to use, and another thing, some amount of parameters we need to fine tune. So those are specific to regularization and optimizer state. So these are the numbers, right? So the beta 1, beta 2, beta so these numbers are we need to take care of that. So these numbers are take care of authors, which is basically they wrote this specific number for their training. So if you are training, you can actually they are just where is the paper? They do, but in GPT-2 paper, they don't give a lot of details about. They didn't give a lot of details about GPT-2, but in GPT-3 paper, they do. They did give us a lot of details about how they really created GPT-3 model. GPT-2 and GPT-3 are not much more different, but GPT-3 model is not an open source model. Their weight is actually the weight of the GPT-3 is never released by OpenAI. And another thing is their you know but they give a lot of details about these hyperparameters and these sort of things really detailedly. So actually they how many models? 1 2 3 4 5 6 7 8, totally 8 models. They released 8 models, but they never released them actual weights, but they create the 8 models. So for very small is the 124 million and 350, then 21 billion, and the yeah, which is the very highest model, 175 billion. OpenAI is the first one who bet on this, but they do give a lot of details about how to create these models, what are the hyperparameters that they used for it. You can see, where is that? So this is one of the data set, HVAC. So it's not a data set, it's kind of like a test, I think. So HVAC is kind of a metric where it is used in 2000s on actually it's a state of the art in 2020 2021 something like that. Nowadays there is huge number of um, metrics you can play with LLM. So Hedgehog is basically where you have a sentence and um, that sentence is basically incompleted and you have four choices. So you can just basically you have LLM and you can give the LLM to that question and it can see the four option and pick one of them. So it's going to be something like that, and this thing is averaged and then we can see whether our LLM picked the right answer or picked the right ones or wrong one. Okay, so these are the things we need to take care, and I think this paper is pretty long. So to 60, they do release some results from the paper. So they do talk about other models as well, part base. So the bird is another architecture. So it's a transformer architecture, but it's a bit different because they used encoder instead of decoder, I think. Compared to nowadays model, it's a pretty old one, but um, for for educational purpose, it's really very good starting point. They done a great job because this is the base for current boom in AI. Because last 5 years there is tremendous amount of advancement in AI. So these are the models. They just and another thing you need to take care is loss function. So that's one of the thing we need to pay attention uh, carefully is the loss function, which is basically end of once the forward pass is finished, you have this you have this function that's basically saying that how good your model is predicts how good your model is predicts the data just loss functions. Many type of loss functions. solutions for regression. So mean square loss, mean absolute error loss, hyper loss. So cross entropy loss. This is one of the famous one, and this is one of the thing we are going to use in GPT-2. I think what they it's just most used binary classification. Cross entropy loss. This is categorical cross entropy loss negative log likelihood. This is the function we just used in we are going to use an GPT-2. Negative log likelihood. So this is how you can use that in using PyTorch. So these are the overall things we need to take care. So okay, here can 8 NVIDIA P100 GPU. So this is all the engineers all you need paper. They use this, and for GPT, it's I don't know whether they said about this. Sorry for smashing my. So zero shot and one shot and few shot. These type of things is basically whether you are giving the giving information in the context or not or something like that. These are the things we basically for checking how good your model is. So GPT-2 is not a actually not a GPT chat GPT thing, not a smaller chat GPT thing, because GPT-2 is they call it as a post training. And the another thing when it's compared to now when it comes to current AI, that current LLM training, there is two sort of training. So basically first you create a model base model. It's kind of where you have a huge amount of data and train it with a specific architecture, and you have a high weights. And that weights itself, it's not going to be very helpful for you, is because we want us some kind of assistant where I take a response and give back a response or something like that. So but that thing alone is not enough to become assistant. So we need to do it's a sorry we are what we are going to do is a pre-training. So we need to do what we need to do is a post training, which is basically a separate part of training. So pre-training is where you have a huge number of data, train it with a specific architecture, and you have a model. And post training is there is a lot of techniques. That's where actual model is converted to a assistant, behave like a assistant. That's where actually the magic happens, is because pre-trained model are just blabbering text. They can talk about any kind of text. They, if you ask about anything, they will they sometimes give the question back to you, and again, something like that. But post training is where actual magic. They use supervised fine tuning, and some people use reinforcement learning for that. There is a lot of things you can do with it. Actually, there is nowadays there is a lot of methods and techniques for to get a better assistant sort of thing, where your behave where your model behave like assistant. So but that thing is basically the the model again going to have a bit of a training, but but the difference is basically you're going to change your model weights a bit, not entirely. You're going to change the model weights a bit, because you are not going to train a model. You are not training a model, but you are fine tuning a model. So where there is a lot of strategy for it, and once you find it, it's going to be like behave like a human. It's the fine tuning is basically fully dependent on your data. So data you're trained with. So if you have data something like a question answer, where you most of the training are done like this, where you have a some sort of a data, something like a question answer, where you have a assistant and you have a human, right? So a human ask a question, assistant response, human ask a question, assistant response. This kind of data, they specifically created this data by humans, or even nowadays the LLMs are good at that, creating that, and they use this data to train other model. So once you train it, once you train it, you are going to have a new weights, not the older weights. You are going to have a new weights, and that is the actual chat model, where you can chat with it, where you can speak with. So this is one of the thing. It's how to say, this thing is basically how I put this. One of the thing where kind of a mysterious in current AI is because whenever you train a model, and the accuracy or something like the loss, validate loss never goes out of this line. So it always follow this pattern. So that's why there is a paper called, I think I can, it's basically for predicting the accuracy, predicting the performance of the model with the model weight, model size, and the compute and the data. If you have three of them and you know about them, you can predict how how good a model you can get out of this. So this is the token counts. So here you can see the common crawl. It have a 4.10 billion tokens, and web text 2 is another data set. Book 1, book 2, Wikipedia. You know, they have a 3 billion data set. 3 billion tokens, not a data set. 3 billion tokens. Tokens is basically where tokens is basically where you have a data and you want to convert to numbers, right? You are specifying you are assigning specific number to specific word, something like that. If you tokens are, you can assign a number to a specific word, entire individual word, or you can number assign to a chunk of something like a VIA is token number 3 and GHT is token number 8, something like that. So common crawl have a 40 410 410 billion tokens, and tokenizer is one of the thing you need to take care. So this thing is specifically specific to tokenizer, based on tokenizer, which tokenizer you are using. Some tokenizer, if you are using word level tokenizer, it might be small. If you're using character level tokenizer, it might be even it might be huge. These are the learning rate thing, and this is our batch sizes where you are doing computation in batches instead of single examples, something like that. It's going to be d hat where um, how many transformer blocks you just stacked. I think D model where it's kind of a, if I remember correctly, it's a context thing. Uh, just see. I think it's a context where how much amount of data it can take. It can, and the model can take at a single time. I think this bottleneck is removed by a lot of before that it's bottleneck. Now the state of the art models I think do not have this bottleneck thing. Just wait a minute. Ten minutes. We've passed 100 minutes. here they mentioned that we use the same model and architecture as GPT-2, including the modification, initialization, pre-normalization, and visible tokenization described therein. Just see the how implemented in Python. Here we have a Python implementation where this is the actual block, GPT block, and this is the GPT configuration where block size, vocabulary size is basically a 50257 is a number of tokens it have. So if this model predicts any token, it's going to be in this 50257 tokens. So that's it. And the number of layers is how many layers you are going to have, stacked layers, and number of heads is attention heads, how many heads you are going to have in a single attention, and number of embeddings size is basically you have a you give you give a vector for each set of tokens, and they do have 768 numbers in it. So the array have you can sort of think it as array that have a 78 numbers, but if you think of it as a vector, it's going to be a 768 dimensional vector. And GPT class and the forward pass, so the weight initialization, and they do some custom things here. And so this is the MLP block, this is the block thing, and this is the MLP multi-layer perceptron, and this is the actual attention thing. And here you can see we are creating three sort of matrix, K, Q, and V. I already said before these matrix, and then we are just and then we will multiply them Here you can see we multiplied with the k transpose and multiplying some number with it. It's for scaling, I think. Then we are just basically masked it, and then we are just using softmax after that, and we just multiply the data attention score with the v, and then transpose, then c project is basically, if I remember correctly, let's just see. So this output projection thing, we need to think about it. Just basically forget about that. What is the output projection thing? Reassemble all the heads output side by side. Okay. Let's just ask about this. Uh, okay, okay, okay. Shape before transpose after reshaping. Okay, okay, okay. I understand. C is the number of heads and number of tails. So we are just basically transposing. So we are basically have another linear layer and multiply it with the output. That's all it's doing. Here you can see we just use a GLU function for activation function, where basically after done a multiplication linear operation, then you have then you basically use some function on it. So there is large number of functions, relu, gilu. There is many type of activation functions, and in this implementation is using gilu. Block size, I think I already explained it. This is where we are creating the token embedding matrix. Then we are creating the positional embedding matrix. and then this is going to be the entire block, and finally you have another linear function, linear matrix and linear multiplication. Then you have a, oh, it's a layer norm, sorry, it's a layer norm. And then you have a LLM head as a linear layer, and that's it. After that, after this you are going to be after that you evaluate to a softmax. And so here this part is basically it's kind of a optimization thing where you are embedding matrix and the attention, um, sorry, the embedding matrix and the, yeah, it's a embedding matrix. The another one is the transformer dot w dot weight. So the last layer hitting. So the last linear layer, this linear layer, and this embedded embedded on the vector matrix, right, where you are creating a 768 dimensional vector for each set of board, that is basically end up in the same set of weight. So if you don't do this, you are going to basically using a two separate space for both matrices. So it's just basically same weight, so you don't need to use two different copies. You can just use a single copy for both of them. That's what it is. This way we are just copying them. Yeah, and this is a forward pass you get yourself, and this is a starting point of the generation where you have some kind of a matrix. Initially it's a single token or something like that, and you have you're taking a device. Device is basically for whether you are going to use a GPU or CPU, and BT is a size of the matrix, and this is for error. If T is lower than, T is bigger than or equal to, cannot be for one sequence of length T, because block size is, so this is the context length. So you cannot more tokens to a you cannot give more tokens to a model. Okay, you cannot give a tokens that is more than 1024. Okay, so that's the limit of this model context. So you cannot give more tokens to the model. So that is what it is. And token data and self data, your token embedding aspect, blah blah blah. And once we finish this forward pass, and it's going to be have a still it's going to be have a token embedding and these kind of things, but only the forward pass, no backward pass. So token embedding and positional embedding, and then we plus them, then we are going to pass through each block, each transformer decoder block, and then this is the last layer of this, and the X is the output. Okay, and then if target is none, if we are given some desired target also, the loss, and this is for loss. So this is for last thing, where you have, where you, after you calculate the value, then you send it to the last function to check how good we predict, how good our model predicts the data, predicts the output. So if target is none, so this is going to be a last layer LLM head, and then it's giving logits are sent to the last function. But if not, we send to the LLM head, and loss is none. So this is for inferencing, where you don't need a backward pass, and this is for training. Then return logits. That's it. So this class is basically for directly assigning, directly download the weights and assigning to our implementation, uh, where you download the weights from Hugging Face, and put it in your implementation. This is where they also implement their, they also have their own implementation, I think. Hugging Face is really the Hugging Face has done such a great job about this, um, maintaining open source community, open source weights, and writing custom implementation for each of them. It's going to be a huge, still it's a free, it's going to be an amazing thing. Yeah, then where we are downloading these are the types model have, and vocabulary size we are setting to this, and that's it. Just basically for if you want to download a model from somewhere else and sync with your architecture, you need to do this. If you're training from scratch, you don't need to do. If you don't, you feel like if you have a plan to training from scratch, yeah, I'm going to do this with how I put this. You are going to do this. Yeah, you don't need this part. Okay. Then this generate part is where generating, and so actually this thing is for validations. Where is it? Where is the forward? So this thing is basically for validation and training, and yeah, no. I think both inference as well. So for inference, we do have some kind of generation implementation here. Then that's it. exactly the same thing, multinomial, then we are picking the last layer and retain the IDX. So this is for distributed data loader where you have a multiple GPU and you need to different GPU need to have a different no different need to have a same data, and we are training no where you have a different GPU, and different GPU have need to see a different set of data, and once you multiply it, once you once both GPU did a forward pass, then it's going to be a sync and it's going to be a backward pass. So once it calculate the gradient, it's going to be average, collect all of them and average them and assign the value to each set of GPUs. So this is for them distributor data loader. This is for that, and this is for B16 and these kind of things where we are changing entire tensor into different format. And pad okay, right module. So these are right tokenizer. These things are or tokenizers and these sort of things. And so this is for learning rate, and this is for basically this is for the GP implementation where you have multiple GPUs and you need to sync them. If you have a 8 or something like 8, and you need to basically wait for the other GPU to complete the job and sync them, and these kind of there is a lot of things you need to take care, be careful about when you train model in multiple GPUs. So these are the these all of the these all of the things is for multiple GPU training, and I think that's it. I think that's it for today. Today we just talked about how GPT created and how we are going to Rust and how we are going to implement in Rust. It's not. I think it's not a simple project. It's going to be a bit complex. Uh, you can see that here because even though you are using PyTorch, it's going to be a bit complex. If you want a GPU support, it's going to be a much more complex. So but we are do try to create it, and now in our live we just talked about everything about how we can create this, and maybe tomorrow we can just dive into the actual project where we are going to write the actual code. That's it. Thank you for watching. If you like our live, if you like our live, please if you like our live, subscribe, hit the like button. If you find it useful, share it with your